So to start the conversation, I'd love to hear about your thoughts during the launch and everything leading up to that.
Oh boy, that's a long story, but during launch, I can remember back to the several launches of rockets and satellites that I've been involved with. I was trying to be as calm as possible and steel myself for the fact that something is going to go wrong. So don't get too disappointed if something goes wrong. And that was amazingly enough and beautifully enough with many of the launches that I've been lucky to be involved with. The launch just went smooth as heck. It was beautiful. It was textbook. They have a countdown for the Falcon 9 that starts about 12 hours before launch. And they went through that entire countdown without a single stop or check. For Chandra, we had checks and stops, but still, and we had to postpone two times. The third time was a charm. So it was thrilling to see the launch go off and see what it was, and that it was perfect. But of course, that's just the beginning, and there were several things that had to happen long before we actually got data. One of the most nerve-wracking ones was IXPE has a boom, we call it a boom, that during launch is compressed, and then once after a week after launch, we extend the boom, and that has to work right. It can't fail. The boom separates the X-ray telescopes from the detectors that are polarization sensitive, and essentially achieves the right alignment and focus, so that this telescope is in front of that detector and this telescope is in front of that detector, etc. So that was really something to be nervous about, and it worked like a charm. It went just perfectly and locked into place. And then the next thing you worry about is, well, what about, will it actually detect X-rays? Will the detectors work? And during the commissioning, excuse me.
Yep.
We had picked out a bright X-ray source to look at, just to make sure things were aligned in detecting X-rays, and lo and behold, of course, so you wouldn't be talking to me if it failed. So everybody knows that it didn't fail, and it's been working beautifully.
Yep.
Since commissioning through today, and we've been getting a lot of data and some beautiful surprises and polarization. We're adding polarimetry, X-ray polarimetry to our astrophysics toolbox, if you like. Two new parameters: the degree of polarization, how strongly polarized is something, and the direction of the polarization, which we call, excuse me, sorry about that, the position angle. So two new parameters that when we look at X-rays from a particular target, all the theories that explain the X-ray emission from that target have to now predict or agree with the polarization that we measure and the position angle. So that's two new constraints on modeling that weren't there before, and we're finding already that we're getting some surprises, and we're finding that we're getting some better constraints on how X-rays are produced. That's really what that mission is all about.
Gotcha. Yeah, we'll definitely talk about the specifics and the science behind it. But back to the launch, if something went sideways, was there a second IXPE? Would we have to start from scratch?
There was no second IXPE. We had spares of some of the important equipment, spare detector and a spare telescope, but not three spares.
I see.
And of course, we didn't have a spare spacecraft, etc., spare boom. All of these things you'd have to. You could build it again, and cheaper because you knew exactly what you were doing and you didn't have to go through the design phase. Just have to put it together, integrate, and test. But no, I'm afraid it would be a big deal. And it's not a given that NASA would want to pay for that.
Right. Yeah, good point. And obviously Falcon 9 performed amazingly, and they have a great track record so far with all their other launches. Did you work with SpaceX closely on this, or anybody at the team, or was it just kind of like hands off and here's our payload and can you just launch it?
No, the IXPE project and our spacecraft contractor Ball Aerospace worked very closely with SpaceX to make sure they understood our requirements and we understood their requirements. So we wouldn't do something stupid and they wouldn't do something stupid. And we had a lot of very good, very impressed with the way SpaceX works and their quality of their people. It was a pleasure. And NASA folks on our side found it a pleasure too. And we had a desire to be in a 600-kilometer orbit, had an inclination near the equator of 0.2 of a degree, and our orbit was 600 kilometers and 0.2 of a degree, practically 0.18.
Wow.
And they just hit it right on the nose, which again is a sign of good engineering and understanding of their launch vehicle and how it works, and it works the way they expect it to.
Yeah, Elon seems to have a good grasp of physics and then applying engineering to this physics and just hitting everything execution-wise to the fundamental of everything.
Yes.
So that's awesome. Did you get to talk to Elon at all?
No, I'm afraid not.
No. But just in the sense of the private industry, I mean, you've been doing this for a long time, and we'll talk about the Crab Nebula in the 70s and what you did there. But leading to this, I'm sure you've seen the whole industry of space technology and rockets evolve. And like, how did you see private industry evolve with it? And like in the future, where do you think it's going to go? And you can talk about the significance as well of that.
Oh, that's an interesting question. I mean, I started X-ray astronomy in 1969 with participating in the rocket launch, which blew up due to a mistake that was made. That taught me something.
Yep.
And through satellite launches, and now with Chandra, it's a shuttle launch and our own engine to take us into the Chandra orbit, which is quite a third of the way to the moon. And its peak and dips down near the Earth, 5,000 kilometers away from the Earth on average for most of its mission. And right now we're actually dipping down very low with Chandra. And then Falcon 9, IXPE was designed actually to launch on a Pegasus, because that's what the announcement of opportunity said, that we would design to a Pegasus. And then, but as a result of the competition for launch vehicles, the Falcon 9 was chosen, and we modified ourselves to be compatible with that. It wasn't too difficult. And these launch vehicles keep getting better and better, more reliable. Marshall itself is involved in the SLS. I'm not, but the center is the biggest launch vehicle that we've ever had, and that'll be exciting. I think there'll be a test launch sometime this year, as I understand it. I don't follow it that closely, just because I'm so busy doing science. I don't have time.
Right. Yeah. Do you think so? Do you think the kind of emergence of the private industry is going to have an even bigger impact in the coming years on how we get things to space? And is NASA maybe just gonna is private industry just gonna maybe take over all the payload?
Well, that's a question of NASA policy and how the president and the agency wants to develop. So I'm just as in the same position really as any other layman on this one. As a scientist, I'm very pleased that we have more variety and choice of launch vehicles, sort of more ways to get to space. And as a scientist, I want to get our experiments to space as rapidly and as smoothly as possible. And if you only have one launch vehicle, you got to wait your turn. If you have two, you can wait less, half the time, if they were all things being equal. And so I think that's a good thing that we have these various companies, SpaceX, et cetera,
Yep.
that are that are coming onto the game. And how the agency decides to deal with that is beyond my pay grade.
Yeah, you just care that the science can be done, pretty much.
Right. I want the science to be done, and make it cheaper to get to space is great. And having competition for that leads to that. That's great. And so I think those are positive benefits. The agency's decisions to increase the private sector's role in launches was a good one.
Yep. So we'll definitely jump into polarization and what it means and IXPE. But just quickly, obviously, IXPE launched in December, just for the viewers, and it's a toolkit. It's one of the toolkits in the toolbox of science that we can now measure polarization of light and different stellar bodies like magnetars and neutron stars, which we'll talk about. But you were working on this in the 70s, in the early 70s. So again, to tie your career back, because we're IXPE is kind of that seminal moment of your career. How did you? How it must have been grueling waiting 50 years for this, but how did you get to that point in time in the 70s where you were even interested in thinking about polarization?
Yeah, we started off at Columbia University, where I was there as a postdoc and then as an assistant professor. I think maybe I was an instructor too. I can't remember that far, but we developed the field of X-ray polarimetry. We thought we knew that scientifically it was going to be important, and we built some early polarimeters and launched them in sounding rockets and looked at some of the bright X-ray sources. And in 1971, we measured for the first time polarization from an astrophysical source, the Crab Nebula and its pulsar, the whole emission from that. That was great. It was 3 standard deviation detection, but that's pretty exciting, pretty solid. And because of that, we were able to put a polarimeter on a satellite mission called the Orbiting Solar Observatory number 8, also 8, and we put a very small polarimeter on that. We confirmed the crab measurement. The sirens outside, fire engines are going by, but I hope my building isn't burning. So I'll have to run. And we confirmed that at the 20 standard deviation level. It was just totally, it was verified. And we were able to compare the polarization with that of the optical in the visible light, and it made sense, the two together. So we established at that time the nature of the X-ray radiation, synchrotron radiation with the magnetic field. And That was in 1975 when the OSO-8 experiments were done. And then my colleagues and I have been trying to put a polarimeter in space for a long time.
Yeah, why after 20 standard deviations and confirmation and it's obvious, why was it still hard to get that done? Was there more pressing matters from NASA?
It's very complex. So we proposed and were successful, the collaboration of, now I was at Marshall with us in Columbia and an Italian group. We proposed to put a polarimeter on a Russian experiment called Spectrum X Gamma. And that was successful. And this was Spectrum X involved two X-ray telescopes and a sliding bench where you could put various different instruments in the focal plane and our polarimeter. So as we thought, two things then happened for the next decade. One was when we thought of better polarimeters and other opportunities, people, and I think correctly said, well, let's wait and see what Spectrum X Gamma does before we commit to another polarimeter, because it's going to be much better than OSO-8, and so therefore might do some serious polarimetry. OSO-8, I have to admit, the only source that OSO-8 was able to do any detection of was the Crab Nebula. For all the other bright sources that we looked at, we only got upper limits, which was sort of not very satisfying and, of course, not thrilling to the rest of the community. The other thing that happened was the Soviet Union collapsed.
Right.
And so the Spectrum X Gamma mission, which was a Soviet mission, was canceled. As an aside, there is currently in orbit a mission called Spectrum X, which doesn't look anything like the original Spectrum X Gamma, but they kept the name the same, I think, to keep the funding easier. Many of the bureaucrats and officials had been used to funding something called Spectrum X, which was X-ray astronomy science. And here's another one called Spectrum X, which is X-ray astronomy science. So they were able to keep it funded, and that launched successfully.
Okay. So I was surprised to hear that you guys worked with the Soviet Union in your early days with NASA. How is that even possible? And was there any friction? I mean, because we hated each other, right, back then?
Well, I think as scientists and engineers, we sort of live in a different world and not a political world. And from our side, we were so happy to getting a launch opportunity, and from their side, they were very interested in the science. And we had that mutual interest in the science and the things you could do with X-ray polarimetry. So we worked together. We didn't dislike each other or hate each other, or in either side. We were just interested in our science.
Science
On the other hand, we can argue, I used to make jokes and saying my polarimeter made the Soviet Union collapse.
Okay. Right. No, that's funny. So yeah, science kind of transcends everything that's happening in the world, because I mean it is important, and it's maybe so important that just to the scientists that it can transcend the politics, as you mentioned. So it's very interesting, because I mean the bitterest of enemies back then, I guess, were the Soviet Union and the U.S., but we were still able to do that. And our partners now, I mean, with IXPE aren't Russia, but they are, I believe, of course, Italy for the detector, which is a big part of IXPE, and then Japan for the mirrors, if I'm not mistaken.
No. We built the mirrors here at Marshall Space Flight Center. The Japanese made a contribution of some filters
Gotcha. Okay.
to keep the heat in from the mirrors, so that their thermal filters very thin, so that X-rays can go through them and not be absorbed. But that was contributed by the Japanese. As you said, we had a huge contribution from Italy, in the form of the polarization sensitive detectors. And that technology was different from things that we had done in the past, and was much more effective and efficient. We're 100 times more sensitive than the polarimeter on OSO 8.
Wow. So did we even have the capabilities of building something like that, or did they have the only detector capable of going on IXPE, or were we able to engineer that as well?
I would at the time they had started their project to develop these detectors in the year 2000. And at the time of the proposals that we wrote, they were the only ones who had a demonstrated and calibrated detectors that worked. And so you don't write a proposal saying, I'm going to build something you're not as successful. Well, here it is, guys. This is what we're going to fly. And so it was a tremendous partnership.
Yeah. So let's talk about IXPE. So obviously, I'm going to try to go over the science behind the detector, and you can correct me where I'm wrong. But essentially, what we're doing is we're grabbing the X-rays from a stellar body that we're measuring. Those X-rays are going through the detector, hitting the mirror, hitting the mirrors, hitting the gas that we have inside, which is dimethyl ether, I think, and separating the electron from the atom. And we take the average of millions of those separations, and we get a vector point. And with that vector point, I guess we can infer polarization. Is that all good? Would you add anything to that?
I would add a little bit to that to help make it a little clearer, but you basically got it. So the X-rays come in and strike the telescope, where they then get focused onto a detector. And as you said, it's a dimethyl ether gas in the detector. And what happens when an X-ray comes into that gas and interacts with the gas atoms, it releases what we call a photoelectron. So it releases one electron that wants to roar off in the gas in the direction of the polarization vector. So if you could only measure where that photoelectron went, you could start to measure the polarization. Now what happens is very nice for that. That photoelectron runs into gas atoms and releases more electrons as it loses energy, and more electrons until you get a big blob or track of electrons. And the detector is designed to image those. So we see an image of the track. And the beginning part of that track, the electrons are in the direction of the photoelectron, i.e. in the direction of the polarization. And so we measure that direction for one X-ray, and then another, and another, and another, and lots, and tens, enough, not hundreds of thousands of them as we've observed the source. And we take the average of all of those directions. And if the average turns out to be 0, it's unpolarized. If the average turns out to be non-zero and very strong, then it's polarized.
Gotcha. Okay. Go ahead. Finish. Yep.
So then we look at the variation of those angles, and if it's very sharp, it's 100% polarized, and if it's just a little bit, it's X% polarized, say 10%. And if the source is unpolarized, then it's very low.
Got it. The big question now is, if something is polarized,
yeah,
we got it and we confirm it with X degree certainty, What is that? What does that mean? What can we then start to infer with that data about stellar bodies or any body that what we couldn't in the past?
Yes. Well, what we can do is add the fact that now that amount of polarization that we measured and that direction that we measured has to be a consequence of how the X-rays are produced. That has to be. And so your theory for how those X-rays are produced has to now predict that. If it doesn't, your theory's wrong. If it does, it helps bolster the belief in a particular theory. X-ray astronomy has gone a long way, especially with thanks to missions like Chandra, which is a super X-ray telescope with fabulous resolution, angular resolution. We've come a long way where in most cases, not only do we know that we're getting X-rays from a particular type of object or particular object, but we've got several theories that claim to explain it. Mm-hmm. They all can't be right, or maybe none of them are right.
Right.
After all, they're only theories. They fit all the data that we've collected so far. But along comes IXPE and gives you two more things you have to explain: the degree of polarization and that position angle. That's the key here. That's what polarimetry does for us.
And you're the principal investigator for IXPE, and I'm just curious what bodies are we looking at? I mentioned some of them, but I'd love for you to go over all of them and kind of maybe which ones are more important, or unless they're all the same importance.
We're looking at a variety of X-ray sources. We're looking at at systems that have a neutron star. That's a star that weighs as much as the sun, but is only about 20, 30 miles in diameter. So gravity at the surface of this star is humongous. And these sources often spin, so their X-ray emission is pulsed. Not just steady, but do-doop, do-doop, do-doop. Yeah. When they were first discovered, it was for a little bit brief time, people thought we were seeing communication from some other civilization.
Because of the uniformity of the pulses, right?
Yeah, the pulses were so nice and regular. You know, what's doing that anyway? Maybe somebody's trying to contact us.
But it's just the rotation of the star.
It's the rotation of the neutron star and how the X-rays are formed. And there are several different classes of neutron stars. Some of them are in binary systems where they're still around a normal star and they orbit around each other, the big normal star, the little little neutron star. And we're seeing X-rays and they're pulsed. There are neutron stars that are spinning that have huge magnetic fields, up to 10 to the 15th Gauss. Really, they've been called magnetars. It seems reasonable.
Yeah.
Coining of a word to describe them. They also pulse, but their fields are so strong that what happens in how pulses are formed, how X-rays are produced in the systems around these magnetars is got to be quite different than normal neutron stars, i.e. non-magnetars with lower magnetic fields. Like the Crab Nebula, the one that we first saw, is about 10 to the 12th Gauss, a few times 10 to the 12th. So other classes, we're looking at a class of X-ray source called a blazar. Now, these are not in our galaxy, but these are out of the galaxy. And they are associated with supermassive black holes at the centers of extragalactic galaxies.
Okay.
So you've got this huge black hole at the center of a galaxy. And this particular one has jets. And we're looking right at the jets.
Mm.
That's why they're called blazars as opposed to active galaxies or active galaxy nuclei. They have all different names. And they're polarized in the optical. And depending on how that works, should be polarized in the X-rays. The idea is that this jet of emission, X-ray emission, is coming towards you. It reaches a point where it shocks with interstellar material or intergalactic material and produces the X-rays that we see and the visible light that we see. It's very bright. And we have looked at with IXPE and we find polarization from a couple blazars. I can't go into much more detail than that because papers are being written and they're being sent to journals like Nature and Science, which don't like the idea of anybody publishing what they are going to publish before they do. So,
Sure. Is there any future possibility of us learning more about dark matter from IXPE or Chandra, but IXPE mainly?
let's start with IXPE or Chandra. The answer is probably. No, that's not a satisfying answer. Maybe if I was smarter, I'd have a Nobel Prize and you would listen to what I say. But it's very difficult to see. We certainly don't see the dark matter directly.
Right.
Obviously, it wouldn't be dark otherwise, but people sometimes forget that. We do see the X-ray emission from clusters of galaxies, which are filled with the hot X-ray emitting gas. If we do the calculations of the kind of polarization we ought to see from those with IXPE, we just don't have enough photons, enough light for enough X-rays coming from them. IXPE, after all, is a small explorer. Small means 200 million, and we, spent the money wisely and well, but it's not a huge super monster mission. Chandra has learned a lot about dark matter. It's a $2 billion mission and has the world's greatest X-ray telescope. And it has seen effects and measured cross sections of dark matter interactions with normal matter, i.e. it's not supposed to happen, and you look to see whether it's happening, and if there's no evidence for it, you know something about the dark matter itself. But no, I'm afraid that unless one of our clever theorists comes along or astrophysicist and thinks of some consequence that would impact the polarization of something that we could look at in such a way that we could trace it to or not to dark matter, that would be great, exciting, super wonderful. But no, right now, we certainly, the 150 scientists associated with IXPE haven't thought of it.
Yeah, it's obviously just so intriguing because it takes up so much of the mass of the universe, and it's ironic that we just don't know anything about it.
Yes.
So, what about Chandra? Can Chandra help in that realm a little bit?
Oh, yes, yeah, Chandra has helped, as I just mentioned. Chandra has put limits on the cross section of dark matter with normal matter by tracing the evolution of clusters of galaxies that are impacted by cosmological models. Chandra has been able to put its OR in and come up with various limits and measurements of things like the cosmological parameters and the density of the universe. So yes, Chandra can and does do that in various different ways, primarily by studying the great clusters and its X-ray mission, as a function of time, cosmological time, looking back in time with very large redshifts, and then closer up with very nearby clusters of galaxies. So Chandra has been a player in that game, and certainly not something we thought of at the time that Chandra was conceived. Chandra's been up there working for almost 23 years this July.
Yeah. That's interesting. You mentioned redshift, which is, of course, the stretching of the light wave, which tells us that the universe is expanding. So without that, we would have no idea that the universe is expanding, but also, I guess, mainly that, how far things are. We wouldn't understand that.
Correct.
How is Chandra doing that exactly? And look at the beginning of the universe through Chandra and discover things.
Yes, we can, just like Hubble and now James Webb, we can look back for deep exposures and see the X-ray emission from galaxies early in the universe. Look and see how they've evolved with time, and therefore put that in terms of the cosmological models and see whether it all fits, etc. And so far, the standard cosmological model seems to be working quite well, including the expansion of the acceleration of the universe being exactly what Einstein predicted, which he didn't believe.
Yeah. And we're also working through IXPE to kind of work with general relativity, and utilize IXPE to kind of confirm some of that as well, correct?
That is absolutely correct. There are binary systems in our galaxy where you have a normal star and the companion is not a neutron star, but it's a black hole.
Oh, okay.
One of the famous objects is Cygnus X1. And we're in fact just finished looking at our first observations of Cygnus X1 a few days ago. And from a theoretical viewpoint, calculations, we can show that the degree of polarization as a function of energy depends on the black hole spin, one of the parameters of the black hole. And so one of the things that we're hoping to do with the data from objects like Cygnus X1 is exactly measure that spin and see what it is. And that will be a big test of general relativity and compare to other methods that have been used, also X-ray methods of measuring a spin, and we'll see if they agree. And from my experimentalist perspective, I hope they don't. Back to the drawing board, but we'll see what happens.
How does a star get locked in with a black hole? How does that even happen?
Well, what happened was that there were two stars orbiting each other in a binary system. One star was dumping material onto the other star because the temperature, for example, produced an outflow of particles, then gravity, because there was this second object nearby with its own gravity and would capture the material, and it would accrete, we call it accretion, and it would accrete more and more material until all of a sudden the star couldn't stand it and blew up. And sometimes, if the conditions are right, when it blows up, it forms a black hole. Sometimes it forms a neutron star where the inner part of that star compresses and compresses, and floomp, it becomes a neutron star, or it can't take it anymore and it says, oh no, please let me go. Blows up and it becomes a black hole.
Wow. And eventually that star will be the black hole.
Pardon?
Eventually, the star will dissipate into the black hole, and then the black hole will get larger.
It may take millions, if not billions of years, because the other star is just sending out a small fraction. We're measuring the amount of material that's left in terms of number of charged particles, not masses. So it's very little. So it's a slow process. But yes, it could happen. Yes, as the black hole accretes more material from its companion from the interstellar medium, its mass gets bigger.
What can IXPE teach us about the black hole in the center of our galaxy?
Well, I got this. It can teach us something very important. It's an experiment that we took data on, and people are working on it as we speak. So I have to explain. So there's the black hole at the center.
Mm-hmm.
It's a very puny, weak black hole as it comes to black holes in the centers of galaxies.
Wow.
Ours is about 1 million or so, several million solar masses, several million times the mass of the sun. Whereas your garden variety massive black hole at the center of the galaxy is more like 100 to 1,000 times more massive. Okay, so we have a puny one. Thank you. Probably good for us. Near the black hole in the center of the galaxy, there are large clouds of molecules. And other X-ray experiments like Chandra have looked to see are there any, and they've discovered that there are X-rays coming from these clouds that are over here, and the black hole is here, so they're not close. And what people think that the reasonable explanation of the X-rays from these clouds is that there are X-rays being emitted from the black hole at the center of the galaxy that are running into these clouds and bouncing off of them, and some of them are reflecting towards us. Okay. Now, if that's true, so bounce towards this sort of triangle of black hole, cloud, and then bouncing towards us. I guess I'm trying to do this so you can see it, but I'm not getting very good at that. If that's true, then that light ought to be polarized. Because if you have an X-ray that bounces off something and goes at right angles to, it'll be 100% polarized.
Okay.
So we're going to look at these clouds to see if those X-rays from them are polarized. If they came from the black hole at the center, given the distances and the intensity of the reflected X-rays, that means that our black hole was much more active several hundred years earlier. Because the amount of X-rays we see are not the ones from the black hole right now. We're seeing the ones that had to travel to the cloud and then travel to us. And the time to travel to the cloud took several hundred years. So polarization would indicate that it came from the cloud, from the black hole, number one, and explain why it was more active several hundred years ago. Right now, we don't know why it should be. Black hole systems like this are very active, and they do vary, but not that much. So we'll learn something. I know it's complicated, but life is complicated. This is not an easy experiment.
No, nonetheless, that's very exciting, because the more we can learn about what it is in the center of our galaxy, the more we can just realize, because the universe is uniform. It's just the same thing pretty much everywhere. A giant black hole and stars surrounding it. So the more we can realize that we can just get a sense of how that even happened, how that uniformity happened.
Yes, there's a lot of similarity and yet a lot of detailed differences, which we have to try to explain all of that.
Yeah. And Chandra. So Chandra, yeah, another one of your achievements. Remind me what your role in Chandra was and the listeners.
And still is until next week. I'm the project scientist for Chandra, the NASA project scientist. So I led the science working group, worked with them, and been involved with Chandra since its inception. Proposal was sent to NASA headquarters in 1976. And I came to Marshall in 1977 to be the project scientist. They wanted someone with some experience in X-ray astronomy. I had already been at Columbia for 77, since 69, 78 years. Published a lot, etc., and was reasonably well known to the other scientists involved. And took the job. And when I got here, I thought, based on history and a mission of this size, when will it really launch? When I got here in 77, it was supposed to launch 8 years later, in 85. And in 78, it was supposed to launch in 86. And in 79, it was supposed to launch, and you get the picture. Yep. It was like the carrot at the end of the stick. It was always, the stick never got shorter.
Yep.
Until the early 90s, when we made some major changes to Chandra. The major change that was the most significant, we got rid of servicing. So Chandra originally was going to be like Hubble in a low Earth orbit, and you could get to it with the shuttle and service it. But the servicing costs, due to the inflation that was hitting us in the 80s and projected out for a 20, 25-year lifetime, were just getting incredibly large. And so we got rid of servicing. Of course, we took a huge gamble that it would work, because if something went wrong, you couldn't go and fix it.
Yep.
But it did work. It worked beautifully as advertised. And so we spent 22 years developing it, which is not unusual, as it turns out. Historically, Hubble was about a 20-year development. Spitzer is about a 20-year development before launch, and not planned, but actual.
Yeah.
And so when I got here, I said, when is it going to launch? I think 2000. I wrote it down on a piece of paper and put it in my desk. We launched in 1999.
Yep, 1 year off. Yep.
Yeah, so I was pretty understood. So that was a very productive period. Of course, during that time, I was trying to design, build, and launch polarimeters unsuccessfully.
Yep.
But I was also working on a scientific cathedral, Chandra, which is proven to be everything that we thought it would, and then some.
So you got the carrot, and then you realized you wanted a second carrot in your head.
Well, we kept thinking of ideas, and we kept proposing them, and this last one was a winner.
Yep.
I think in part because Explorer missions, you really have to show that you know how to do it. And we had our group had built X-ray telescopes of the kind that we needed for IXPE, and they're flying, actually currently flying on the real Russian mission, Spectrum X, and successfully. And the Italians had built and tested their polarization sensitive detectors. So the main technology, other than the spacecraft, of course, and the launch vehicle, were demonstrated. And so we finally got that thing just in time for my retirement.
Yeah, perfect. Yeah, so you got your carrots and two amazing feats. And obviously Chandra got the Nobel Prize.
Yes, Roberto Giacconi, the father of X-ray astronomy. He actually conceived of Chandra 1 year after he had discovered the first X-ray source.
Oh, that's impressive.
Yes, just a tremendous, insightful. Ricardo Giacconi was one of the most insightful people that I've ever had the pleasure to deal with.
A fellow Italian, so that gives me some pride. Let's talk about life, because life on other planets or moons or anything, because obviously IXPE can't really help in that sense a little bit
No, I'm afraid not.
But Chandra can.
IXPE can't, Chandra can. IXPE, there again, it's a small mission. We just don't have enough collecting area. The number of X-ray sources, the number of X-rays from stellar-like sources is orders of magnitude below that which we see from the objects that we're looking at with IXPE. On the other hand, they're easy to see with Chandra, and measuring the X-ray emission from these stars, normal stars, tells us whether or not a planet's atmosphere can be maintained. If the star is too bright in X-rays and the planet is too close, you're going to blow away the atmosphere. So you can put an Earth close to a much more active source than the sun is, but you can put it at the distance that it is. So one of the things that Chandra is doing together with people who do the planetary finding is going through and look for the X-ray sources that are coincident with this planet and see whether or not they're too bright for it to sustain life.
Wow. So it's not necessarily looking for signs of life, but if a planet can be categorized as possible inhabitant.
Right.
Okay.
Could be. It helps the categorization of whether this planet that's been discovered by other means is possibly to have life.
And then by the time we have a detector that can jump into a planet and analyze everything, we'll have all this data of which ones to choose from the myriad of tools we got.
It helps.
Yeah, it helps.
Focus the search.
So I talked about it in a previous video with Dr. Slava Juristchev from JPL, and he agreed with me. And I'm curious to see your stance on life. But my stance on life is pretty simple, and it's with three elements, and that's the uniformity of the universe. So it's made of the same stuff everywhere, and obviously life, carbon-based life. Carbon's huge in the universe, and then space. Space is giant. There's tons and tons of space, so enough. A larger sample size, even if life is rare in a certain area. And then, of course, time. Life on Earth, 4 billion years. Universe, 13.8.
Yeah.
So those three things, to me, point that there's no reason why we should be special. So I'm curious to hear if you have, obviously you're a scientist, so you don't like to speculate, but I have to ask you to speculate a little bit. I'm curious to hear your thoughts on that.
Right. So now I'm going to speak as a non-scientist.
Right. Exactly.
And I've always felt, for reasons similar to your reasoning, not the same, but similar, that there must be life elsewhere. I mean, there's just, the numbers are too huge of the probabilities. Planets, You know, people didn't think it 3 years ago. We didn't think there were that many planets per star. Well, that's blown out of the water. And what about life-bearing planets? Well, if they're Earth-like, they certainly have been proven to be, you know, et cetera. So again, for all of the kinds of reasoning that you just gave, I certainly believe there's life out there.
Yeah.
And if that was my goal, I would be a radio astronomer.
Gotcha. Yeah. Do you think radio waves are the number one form of signal we can probably count on as a life sending us something?
I think the physics of it is in favor of it. That it's easy. I mean, look at what you have to do to build even an IXPE that can't even detect anything from a normal star, right? It's very complex technology, but we've been dealing with radio. We've been building radio transmitters for years, and radio antennas, receivers. And so we discovered that, oh my God, the universe is filled with radio waves. So I think it's reasonable, but then my daughter is a publisher of science fiction. She's
cool.
She's the owner and publisher of Bain Books. I'm sorry to give the advertisement, but feed my granddaughter. And she got a large audience that has many ideas about this.
Yeah. Are you kind of like, for some of the books, maybe the science guy that gives her ideas and helps in some sense?
No, I don't. I'm the one who interested her in science fiction as a child. Tolkien, etc., and various things. And then I sent her to college while she was going to cons, they call them. But now look, she's a successful publisher and editor of books. So it was a wise move on my part. Yeah,
definitely. Yeah, I'm a big Tolkien fan. So yeah, I back to the life thing. I'm glad to hear you agree. It's really split in half. Some people are really not pessimistic because it's not a negative thing, but just are kind of like, I don't think so, and some people are. Yes, I don't think they've visited this planet. If anything, you know, if any of those videos or whatever, especially the kind of the big ones that are out there that have a lot of, I guess, claim to them, they could be just sensors that are just sent to map the universe or something. I don't think they would, if they have the technology to get here, I think they also have the technology to do what they want to do without physically being here. So maybe they're just our IXPEs or something.
Right. Well, we need some new, you know, the technology to get here, even from the nearest stars, is so improbable that.
I see.
And that's why I said, you know, radio astronomers, I'd be looking for signals. I'm not going to look for any direct evidence. It's a waste of time.
Yeah.
We don't have that much energy available.
Right. So to the energy required to just get to the nearest star system is so far above. Yeah, I see. That's a great point. So maybe life in the universe was destined to just never meet and be in their own little buckets of the universe.
Yes, but we might be able to communicate with long time differences between hello, wait for years. Hi.
Right. Because it can only be the speed of light. That's all. That's the fastest. I mean, even less than that. But and even then, we by the time we get hello and we send something back, they could long be done, hit by an asteroid or something. And it's a very solemn thing, the speed of light and how it goes. You know how it goes through the universe, because we're seeing objects. And we're getting data from objects that could not, they're probably not even there anymore. And it's It's very interesting to be a human in that environment, and I'm grateful we're able to make these detections, but they're just, it's so far that like even light is nothing compared to those distances.
Yes, that's something that is hard for all of us at times to get our hands around.
Yeah.
Yeah.
Yeah. So, great. Well, you mentioned your next steps kind of to me, but I'm curious to hear. You're officially retiring next week, right?
On the 31st of May. So,
wow.
And it's getting pretty close.
Yeah. Yeah.
But I am becoming an emeritus. It's a formal NASA position.
Mm-hmm.
It allows me to keep coming to work and keep my office and my iPhone and stuff like that. And
yeah.
But I don't have any of the more, I would say, necessary duties that my previous positions required. So I'm not going to be involved in budget discussions for either mission, and et cetera.
Well, you gave him enough. I mean, you gave him IXPE and you gave him Chandra. So, I mean, I'm sure they're not asking more of you, and you're doing this because you want to, which is great. And I'm assuming you'll be doing the fun stuff. And now, since you've earned this, none of the annoying stuff. So
Exactly.
mainly, yeah,
exactly, right. And for that, however, I don't get paid.
Yeah, gotcha. So who's taking your place when you do leave for Chandra and IXPE?
Okay, for that, this isn't. The center has recommended, so my deputy PI on IXPE has been recommended to become the PI, and my deputy project scientist on Chandra is recommended to him to become the project scientist. So we have obvious succession.
Gotcha. In addition to that, some like, I guess, part-time stuff with NASA, what else are you going to be doing? Do you like to fish? Do you like to, I know you like to spend time with your grandchildren. Do you like to golf? Do you like to do anything like that?
Well, I think physically, some of those, I used to play basketball until I was 68.
Wow, nice.
But I'm afraid that's out of the question now. My wife and I have been playing tournament Scrabble for years.
Oh, nice.
So that's something that we'll be doing and going to tournaments, at least to be thinking about it. We stopped during the pandemic, so haven't studied for years, a couple of years, 3 years now.
Are there any cosmological words that you were trying to use, but they weren't in the Scrabble dictionary?
None that I can think of.
Oh, that's good. That's good.
The Scrabble dictionary, like the universe, keeps growing.
Right. Yeah. Awesome. So this was great talk. I want to end with something. You mentioned it when we chatted, but there's a discovery about I think a magnetar that you guys were looking at. How much can you talk about that? I can
give you some hints.
Okay.
Yes, and the paper was submitted last week, in fact, to Science.
Congrats.
So we looked at one of the magnetars. It is polarized, and the behavior of the polarization as a function of energy is very interesting. I will go so far.
Okay. All right. We'll have to see. So we're going to be able to read about that in Nature, correct?
Science.
Oh, Science magazine or Science. Okay. Gotcha.
Yep.
Awesome. Cool. Well, Martin, we'll leave it there. That's a nice little cliffhanger and teaser for the audience and for myself. So thanks again for doing this. And I can't wait to see what you're up to after retirement, and congrats on that. And I just wish you the best of luck.